But let's start the lecture. Okay, so last time we finally introduced ourselves to the concept of a limit. Will you shut that door, by the way? I noticed it was, I think I saw a glare in the video from it somehow. Yeah, I don't see your vantage point. I only see from here where there's no glare, except for the windows a little bit. Anyways, so we had this idea of a sequence converging. Do you remember what a sequence is? Maybe we should start with that.
Yeah.
What's a sequence?
It's a list of numbers.
You can think about it as a list of numbers, but what's a sequence? It's a function whose domain is the natural numbers. So it maps 1 to something, and 2 to something, and 3 to something, and 4 to something. Maps all the natural numbers to a number. It's a function whose domain is the natural numbers. That's what a sequence is. Now we only bother writing down the range, and we write them in the order. What does 1 go to? What does 2 go to? What does 3 go to? What does 4 go to? But ultimately, a sequence is a function whose domain is the natural numbers. Does that make sense? Make sure that makes sense, and then we'll make sense of this definition. So we wanted to say that a sequence converges to a number A. A sequence AN is said to converge to some number A, provided that for every positive number you pick, or for any positive number you pick, you can think about it that way if you want, for every positive number or for any positive number, there exists some natural number such that the distance our sequence is from that number is less than that positive number from that index on. This definition is going to come up again and again. You're going to struggle with it every time you see it again. And you've got to just wrap your head around it. So I want to reintroduce that definition and then do a proof one more time using it before we continue that we did last time. A nice easy one. Now remember, what does it mean for A minus A to be less than epsilon? That means that the distance between these two things is less than epsilon, right? So another way that we think about that is AN is in between A minus epsilon and A plus epsilon. So maybe one more visual way that we see that is AN somewhere right here. Here's A. Here's A minus epsilon. Here's A plus epsilon. We're saying that the sequence, it might start out clear out here, but eventually, if we keep plotting all the points in the sequence, there comes an index such that from that index onwards, all the points in the sequence are within epsilon of A. That's what we're saying. Does that make sense?
Yeah.
This definition, it's so crucial, and it's like we're only adding to this definition from here on out. It's not going away. It's not like, oh, maybe I won't get that, but I'll get the rest of the class. No. If you don't understand this, you don't stand a chance with the rest of the class. So let's make sure that this makes perfect sense and go over it as many times as we need to.
Makes sense algebraically.
But do you have intuition for what it's saying?
You're saying that AN, okay, so it doesn't matter how big your sequence is, AN is always in between A minus epsilon and A plus epsilon.
So AN represents some sequence, right? It could be the sequence. Let's do the one that I did right here. Let's try that sequence. That sequence is 1, 1/2, 1/3, 1/4, 1/5, etc. Right?
Yes.
Don't need that. That's how we write that sequence. I'm saying, and my claim is that that sequence converges to 0. So I'm saying no matter how small of an epsilon you pick, I can eventually find an index in this sequence such that for every term from that index onward, that sequence is within epsilon of 0, or A. So I claim this converges to 0. So I claim A is 0. The sequence converges to 0. So I claim that eventually this sequence gets as close to A as I want. I'm claiming that the distance between the terms in this sequence and 0 becomes as small as I want. So for any epsilon you pick, I can eventually find a term in this sequence such that for that term and from that term onwards in the sequence, I'm always within epsilon of 0.
Isn't that?
That's what I mean by this converges to 0.
Isn't that
Why does
exactly
it
what
have
the
to be
limit is?
positive?
Yeah, this is, yes, sorry, should have said that to begin with. To say a sequence converges to A, and to say the limit of the sequence of A is the same thing. Okay, so I'm going to go back and forth between that terminology. Sequence converges to A is saying the same thing as the limit of the sequence of A. Now, I might accidentally say one or the other, and I just realized now I said converges here and did the limit here. Same thing. So do you understand that?
Mm-hmm.
Right.
So I'm going to switch back and forth with my terminology.
Sequence A and converge to.
Yeah, so a sequence AN is said to converge to A, or the limit of a sequence AN is said to be A, if this is true.
So just, okay, yeah.
Now you said, why does epsilon have to be positive?
Yeah.
It's a distance.
It's a distance. The distance between these has to be less than epsilon. A distance is a positive number. This is a positive number. A positive number can't be less than a negative number. So what I'm saying is, pick a distance, any distance you want, which is the same thing as saying pick a positive real number. So no matter how small the distance you pick, I can always find an index, big N, such that my sequence is always within that distance of A. Right? So let's think about this example for a second. I'm saying pick any distance you want. Say you pick the distance 1/4. Right? I say, aha, then for n equal to 5, from this index onwards, my sequence will always be within 1/4 of 0. Right? Notice that's not within 1/4 of 0, that's not within 1/4 of 0, that's not within 1/4 of 0, that's not within 1/4 of 0. But from this term onwards, my sequence is within 1/4 of 0. And that would work for any positive number you pick. For any number you pick here, I can eventually find a term in this sequence, so that from that term onwards, the sequence is within the distance you picked of 0, the thing it converges to. Is that making sense?
Mm-hmm.
Yeah.
Feel like you got it?
Yeah.
So let's do one more small proof before we continue into class. Proof we did last time, nice simple proof. Let's prove that the limit of this sequence is 0, or in other words, this sequence converges to 0. Okay? And you might see me write the limit as A goes to infinity. You might see me just write the limit, or you might just see me say this converges to 0. Well, they're all saying the same thing.
Okay.
Okay? I think the author does it this way. So we'll try to remember to do as n goes to infinity. Anyways, so let's do this proof. So we need to show that this definition holds for any epsilon you pick. So let epsilon be some positive real number. Doesn't matter what positive real number. It can be any positive real number. By the Archimedean property, I know that there exists some natural number n, big N. There exists some natural number big N, such that 1 over big N is less than epsilon. Right? Just using the Archimedean property directly there. Then I make a side observation. I say, look it, the absolute value of 1 over n is equal to 1 over n is less than 1 over big N for all n greater than or equal to big N. In other words, as n gets bigger, the term gets smaller. Right? So that's a side note. So remember ultimately what I'm trying to show. I'm trying to show that the absolute value of 1 over n minus 0 is less than epsilon. That's what I'm trying to show. Once you pick an epsilon, I need to find an n such that this is true for all n greater than or equal to big N. So we observe this fact, and then boom, we're basically done. So 1 over n minus 0, or an minus a, is less than epsilon for all n greater than or equal to n. So remember, 1 over n was less than epsilon. 1 over little n was less than or equal to 1 over big N. So that, which is the same thing as that, is less than or equal to this. That's less than or equal to that, so that's less than or equal to that. And since this is less than epsilon, this is less than epsilon.
Okay,
For all n greater than or equal to that big N. So from that index onwards, this absolute value is less than whatever epsilon you picked. Pick an epsilon, I find big N. Now this is true for all little n greater than or equal to that big N.
What happens when we get a proof that says, proof that, or just solve the limit of 1 over n? You can't prove anything.
Solve.
So, wait. That's a good question, because a limit, or you only prove something that's a statement. Okay, never mind. I was just confused about why we ended up writing 1 over n minus 0, and we replaced that for a. A is always our solution.
A is what it converges to. It's whatever's on the other side of the equals. AN is the sequence that you're talking about. So I rewrote it as AN minus A. In this case, it happened to converge to 0, so we didn't need the minus 0. But we could have made one that converges to 3, and so it would have been minus 3 right there instead. Right?
Alright.
So there's a refresher. Hopefully that's bringing up some good memories. Remember that one time?
Yeah,
So cool.
I do remember it. It's cool.
Alright. So, the last thing we went over last time was the comparison limit. Right? Draw some lines in this so we can. Oops, that was part of that. Start seeing separate thoughts. Okay. So the comparison limit was the last thing we proved last time, and so I'll write it up here again real quick. It was that. I'll just try it like this. So this is what we proved at the end of last time, and it was that if the limit of AN is equal to A, comma, and if there exists C greater than 0, so some positive real number C, and some index N1, we'll call it, such that the absolute value of Bn minus B is less than or equal to C times the absolute value of AN minus A for all n greater than or equal to n1.
So C is a constant, greater than
Yep.
0. Positive constant.
Comma. Then the limit of Bn is B. So let's make sense of this. So if we already have some convergent sequence, and if this sequence is always less than or equal to our convergent sequence by some factor of C, starting at some index onward, then this also converges to that. Does that make sense? Okay. Think about what it means for this to converge. If this converges, then eventually there's an index where this thing's less than epsilon. Right?
Mm-hmm.
Which means that there's eventually an index where this thing's less than epsilon.
Okay.
Which means that this is going to be less than epsilon for that index onward as well. That's kind of how we went about proving it.
Right.
I'm not going to reprove it here. You
No.
have that. It would be really useful, you guys, if you'd watch like the last 10, 20 minutes of the lecture from last time before or something. Maybe for some of you, rewatch the whole lecture. Jacob.
Oh, okay.
To get caught up on these things, because I'm always going to do a quick recap of what we did last time. So that's the comparison limit, and we're going to use it for our proofs today. So that's all review material. Now we're starting new material. And I think the first thing that we wanted to prove was that the sum of the limits is the limit of the sums.
Easy.
And for those of you that are in calculus, you'll recall these things and you use them all the time. So prove that the limit, as n goes to infinity, of an plus bn is equal to the limit, as n goes to infinity, of an plus the limit as n goes to infinity of bn. You understand what we're proving?
Yeah.
The way that you typically say this is that the limit of the sum is equal to the sum of the limits.
Wait, no, doesn't an and bn have to be a series?
Yeah, they're series.
Okay.
Not series, sequence, sorry.
Or sequence.
Series is a special sequence, right?
Right.
We went
It's
over that
a
last time.
summation sequence.
Yeah, a sequence is a series of partial sums that you make out of some given sequence. Alright, so let's do this proof. So 1, let an be a sequence that converges to A. I didn't add a part onto this I should have added, so sorry. It's if this is a convergent sequence and this is a convergent sequence, then this is true. Right?
Okay.
It doesn't make sense for this to be true if this doesn't have a limit or this doesn't have a limit. So I should have specified that. If A and B are convergent sequences, then this is equal to this. Does that make sense what I didn't write it there?
Yeah. Well, that's obvious.
Obvious is a hard word to say. Let me tell you something. If you get a math degree, the thing that is going to just frustrate you more than anything is when an author's writing their textbook and then they say, and obviously, and put some conclusion there. You're like, what do you mean obviously? How the heck did you get from here to here? And you've got to do like 4 lines of proofs in between to make the connection in your brain. Like, stupid author, put that in there. Obviously. Makes you want to punch him. It's not obvious. Stop pretending like you're so much better than me. Might have been obvious to him, right? Obvious is a hard word to say. Things that are obvious to one person are obvious to another. Okay. So let A be a sequence that converges to A and B and a sequence that converges to B. So we have these two convergent sequences. Right? Now, ultimately, what are we trying to show? Let's do a little bit of scratch work to the side. We're trying to show that this is equal to this. So in other words, we're trying to show that the limit of an plus bn is equal to a plus b, right? Because that's what that is and that is. And how do we show that that's that? We need to show that the absolute value of an plus bn minus a plus b, maybe I'll use parentheses to help you see all the thinking, is less than epsilon for all n greater than or equal to some n.
Okay, so
this is ultimately what we need to show. If we can show that for any epsilon you pick, this inequality is true starting at some index n, then we're done. So this is ultimately where we're trying to get, right? We need to use this definition right here, where this is an plus bn, and this is a plus b.
right.
Okay.
So do you understand, ultimately, you see how this is like the last line of our proof?
Yeah.
If we can show that this is the case, we're done.
Yeah? No? What?
So, an plus bn is just a sequence, right?
Mm-hmm.
Here's a sequence, an plus bn.
A sequence plus a sequence.
And I'm trying to show that the limit of this thing is this, which is a plus b.
A sequence.
Maybe that's where I should have started. Are you good with that? This converges to a,
Yes.
so this is equal to a.
Yeah.
And this is equal to b.
Yeah.
So I'm trying to prove that the limit of this is equal to a plus b.
So the limit of a plus b is equal to the limit of a and the plus the limit of b.
Sure.
okay? And
So I'm trying to show that this is equal to a plus b. So just taking that
oh,
line.
okay,
You good with that line of thought?
yeah.
Now plug this directly into our definition. To show that this is equal to this, I need to show that this is true. No matter what epsilon you pick,
Okay.
starting at some index n. Just using this definition directly.
Okay.
This is how we show the limit.
We know that the sum of two sequences is a sequence.
Yeah.
Okay.
I mean,
Why is that obvious?
the sum of two functions is a function. I mean, that's just telling you how to get a term. Plug in 1. Can I plug in 1 to that? Yeah. Do I get a real number out of that? Yeah. It's like we know that adding real numbers together produces a real number.
Like separating a function into two parts. Also.
Yeah.
So you're good? This is just another way of writing this
Yeah.
sum sequence?
Yes.
Okay. No, it's a good question. Make sure it makes sense in your head. Okay. So, and this is ultimately where we're trying to get, right?
Mhm.
Okay. So I know that AN converges to A, and I know that BN converges to B.
Then.
And
it's a plus.
probably should start with a let epsilon. Hold on. Let that. Let that, and let epsilon be some positive real number.
Is that a plus?
That was an and. And? Ampersand? Okay. I don't know, how were you used to seeing it?
I use it like 3.
Backwards epsilon with two lines.
Is it like that?
Yeah.
That's not the right one, but I can't write the right one, so I do that.
That's what I do too.
Yeah.
Alright, I'm just trying to say and. In a little bit of space. And let epsilon be some positive real number. Okay? So if AN converges to A and BN converges to B, what does that tell me?
Then AN is B, or AN is A and BN is B.
So then, maybe say it this way. Then there exists some natural number, call it n1, such that AN minus A is less than epsilon for all n greater than or equal to n1,
Oh yeah.
right?
Yeah.
And
Exists another index.
there exists n2, sorry, in n, such that Bn minus B is less than epsilon for all n greater than or equal to n2.
This looks a lot like our last.
Oh, I may want to do epsilon over 2, sorry. So I'm going to be adding these together.
Yes, we agree that epsilon over 2.
Epsilon over 2 is just another positive number, right? So I know that for any positive number, this is true starting at some index n1. And I know that for any positive number, this is true starting at any index n2. That's what it means for them to converge. If they converge, that means that I can make this inequality true for any positive number there starting at some index. So this is just writing out the fact that AN converges and BN converges. So I haven't lost you here, have I?
Mhm.
We're good with these two lines? Alright, perfect. Then let's add them together. Then, was that the way I did it? Oh, sorry. I need to start with this and then work my way using these. So let me write it and then walk you through it. Minus. Is equal to, let's see, get my A and my A together. And then triangle equality. sorry. I have to stop right there. Can't set less than epsilon unless I have index. Okay. So, let me give you some thinking that you should be trying to use to figure this out. So I know that this is less than epsilon halves, starting at some index, and this is less than epsilon halves, starting at some index, right?
Yeah.
And I need to show that this is less than epsilon, starting at some index, right?
Good.
So I knew that I needed to manipulate this somehow to get this term and this term to show up. That's my first step. I don't know what this is, but I know what this is, starting at some index. I know what this is, starting at some index. So I need to manipulate this to get these two things to show up. This is my first step. So I'm just playing around with it, trying to get those things to show up. I group my AN with my A, I group my BN with my B, and then I use a triangle inequality. You get up to here?
I just
Yeah.
subtract.
Right now it's just manipulating an algebraic expression. Huh?
I just subtract A and B in.
Oh, sorry. Thank you. That was not intentional.
Oh, I thought that was how it was supposed to be.
No, AN plus BN. AN plus BN.
Okay.
AN plus BN. This is the sequence we're talking about. So the sequence minus A plus B, and then this is just an algebraic line. There's nothing else going on here but algebra. This has nothing to do with limits. This is just algebra.
Has nothing to do with that step 2.
Has nothing to do with step 2.
Okay.
It's just another observation that we're making.
Okay.
Because now, and I'm going to make one more observation, then we're going to kind of bring it all together. So for, not observation, but one more definition. Let n equal the max of n1 and n2. So, the reason that I do this is because I need an index where this is true and this is true. Because remember, this is only true starting at n1, and this is only true starting at n2.
Right.
I need to find an index where both of these are true. Both of these are true at whatever is bigger out of these two. If this is true from 7 on, and this is true from 13 on, then both of them are true from 13 on. Does that make sense?
Yeah.
So whatever this n is, both these are true for all n greater than or equal to just big N now.
Right.
You see that?
Yeah.
And that's the index that I wanted. So then, this is true for all n greater than or equal to big N, whatever the max is. And this is true for all n greater than or equal to that big N. Right?
Yeah.
Now combine it all. 5. Then this.
When you say max of 2 numbers, it's just saying whichever one's bigger.
Yeah, whichever one's bigger. Sorry, I thought that was...
You went over it last time, just make sure.
Okay, yeah, it's whatever's bigger out of the two numbers.
Okay, you keep saying that you need an index. What do you mean?
So right here, we need to show that for any positive number you pick, I can find an index
So an index
such that this distance is true for every term in the sequence from that index onwards. The distance between the nth term and what it converges to is less than the distance you picked for that index onwards.
So you're saying your index is n.
My index is going to be n in this case, yes.
Okay.
This is going to be true starting at that n, that index.
She's talking
So
about
for like any number you choose, right? Because that's what the n is.
No, epsilon's what you choose. For any distance you choose,
Okay.
I can find an index
that's bigger than.
so that this distance is less than the number you chose.
Okay.
From that index onward.
Okay.
Does that make sense?
Yeah.
These are good
So
questions.
when you were using the 1/4, your index was 1/5 onward.
Was 5.
Was 5 onward.
5 onward. N was 5 because 1/5 was within 1/4 of 0.
Okay.
From that point onward, 1/5 was, 1/6 was, 1/7 was, all the way onward. Every other term in the sequence, starting with the 5th term, was within 1/4 of 0. So it converges to 0.
Okay.
Good? These are great. Keep asking. You're going to get confused again, then ask, and get confused again and ask. All right. So, recapturing this line and combining it with the logic of these lines using this n. Sorry, I'm kind of blocking your view. So an plus bn, our sequence, minus what it converges to, or what we're trying to show it converges to, is less than or equal to an plus minus. Using this line, right?
Yeah.
So that's kind of the crux of the proof in one line.
Okay, so what you did is you used number 3 and number 2 and wrote out one line.
So yeah, kind of. So I used number 3 and number 2 using the index in number 4.
Okay.
So let's go over real quick. Maybe I should have written this as number 2 and worked my way down. So pick the max index of n1 and n2. Right?
Okay.
If this is true from n1 onward, and this is true from n2 onward, then both of them are true from n onward.
Okay.
Because it's the bigger index.
Mm-hmm.
Right? So then, this is just an algebraic statement that happens to be true. So here we apply the algebraic statement.
Mm-hmm.
And then we're saying we know that this, and then we're using this logic. This is less than that, and this is less than that,
As soon as
for
you
all n greater than or equal to n.
Okay, so you just proved it.
Yeah, so we just proved it. There you go, that's the proof in one push here.
So you had to manipulate your algebraic equation until it could imply to.
Well, here I'm kind of just writing out what I know up to
I
this
know,
level.
right.
Right?
Mm-hmm.
And I could have gone down and I could have said, you know, something like, I could have come down here and put 7. Therefore, the limit of an plus bn is equal to a plus b. What does that mean? That means I would have to have a 6 where I said, then the absolute value of
And minus a.
So let's walk through some of the thinking we could have done in constructing this proof. So coming from the top, I could have gotten to here just fine. That's just using definitions to line 2, right?
Mm-hmm.
And I say, I don't know what to do. Let's go to the bottom. I know here's what I'm trying to prove, right?
Mm-hmm.
And I know that this being true means this is true,
Right.
right?
Right.
So now the whole goal becomes, you need to find this n. Right? And I have to use what I'm given to do it. So I know I've got to use this, and I know I've got to use this. And here's what I'm trying to prove. So how can I use this information? How can I use this information? The only way that I can do that is if I can somehow get this thing to show up and get this thing to show up. So 3 was just getting these two things to show up.
Right.
4 was finding my index. And then 5 was the big leap that you just have to make. I don't know how else to say it. I mean, when I wrote these, I knew where I was going with the epsilon halves and the epsilon halves. You wouldn't have known to put epsilon halves and epsilon halves there.
Yeah.
So when you're actually doing this, you kind of hold off writing this line you just have in your head. You have that this is less than some positive number, I don't know what I'm going to put there yet. This is less than some positive number, I don't know what I'm going to put there yet.
But they're so.
Then I do this work right here, right?
Yeah.
And then that's when I realize, oh, I'm going to have to add those two things together, and I need them to be less than epsilon. So I need each of those things to be less than epsilon halves. Now I'll do another proof where we multiply them together so that you can see. Because if I have two terms and I'm multiplying them together, what am I going to make them less than? Square root of epsilon. Right? Because then I want square roots. Whatever I'm making them less than, it needs to come out to epsilon. So So if I'm adding them together, it needs to be epsilon halves. If I were multiplying together, it would be square root of epsilon.
Right.
If I was timesing it by 6, it would need to be epsilon over 6. Good?
Yeah.
Some of these, I mean, there's just no trick to telling you how to do it. You just got to do them. And you start to realize what to look for through comfort with them. I don't know. I don't have any, this is what I always do, because there isn't any, this is what I always do. Okay. Let's do another proof. Probably fit right here. It's only a 2 liner.
Is this a corollary?
It comes, it's like a, I don't want to say a corollary of a lemma, but it's basically just using the comparison lemma directly. So we have,
Janetta, do you have the syllabus?
Yeah.
Let's see.
here,
Are we ever going to do test 4? It was 2.1.
yeah, we're going to continue through your homework exactly wherever you're on.
Okay.
We're not skipping any homework. Let's make sure that that's really clear. You need to do all these problems.
Right.
It's the only way you're going to learn the materials, to do all the problems.
Well, we can just do test 4 at this time.
I don't care if you combine your homework when you do it. Just make sure to give me 3, 4, and 5. You guys are way behind on homework.
We're 1 test today.
And after today, 2.
After today, 2.
Yeah.
Yeah. If you count this behind, I mean.
So let's get caught up.
Okay.
And then obviously I'll be here after school. Okay. So, if AN converges to A, then AN times a constant converges to A times n constant.
Oh yeah, this is what
Right?
in calculus. Yeah.
The limit of a sequence times a constant is just that constant times the limit of the sequence, in other words. So once again, this was something that you used in calculus over and over again when you did it. So let's prove this. 1. Observe that absolute value of alpha AN minus alpha A is equal to the absolute value of alpha times just simple algebra there. Make sure that makes sense.
Observe that alpha A. Yeah, you can factor it out, and then when you're times it.
Yeah.
I'm going to write one more thing here so that we can see the comparison limit directly. Kind of a trivial statement there at the end. That is less than or equal to itself.
Okay.
Okay.
It's equal to itself.
Huh?
Equal to itself.
Yeah, so it's less than or equal, since it's equal.
But it's also greater than or equal.
That's fine. We just need to make sure less than or equal is true. Look at our comparison limit. We need to show that this is less than or equal to this. Right? So, then basically say that we're using the comparison limit. So, since the absolute value of alpha is greater than or equal to let's make sure you see it. And then, so we know that AN converges to A, right?
Okay.
So we know that AN converges to A. Sorry, we're looking at, this is kind of, well, we're looking at this is less than or equal to this if you want to see the comparison limit directly. So maybe go over the comparison limit. If we want to know, does this thing converge? The comparison limit is showing for that Bn converges to B. So if we can show that Bn minus B, oh, I missed a line. For all n, or we could say for all n greater than or equal to 1. Okay. So, let's make sense of this over here. Comparison limit says, if you have something that converges AN, if you know that AN converges to A, it's for showing that BN converges to B. So we know that BN converges to B, and if you can find some positive number C greater than or equal to 0. So if you can find some non-negative number C, so that this is less than or equal to this, starting at some index, then Bn converges to B.
Okay, but I don't see how we're using that here.
Yeah.
So here's our reason. This is Bn, this is B.
Okay.
So we're saying Bn minus B is less than or equal to some non-negative number times An minus A, which we know converges.
No, An minus A is just our original B.
No. If the limit of An equals A,
Okay.
so we know that An converges to A, prove that this converges to this. So we're trying to show that Bn converges to B. We know that An converges to A.
Right.
So we have the absolute value of Bn minus B is less than or equal to some positive number times An minus A for all n greater than or equal to 1.
Why?
In this case, we could just start at 1. This is always true.
Natural numbers.
For all natural numbers. We just need to find an index where it was true. This is true from the first index onward.
Since
Okay, where
a
I'm
constant
getting
is greater
confused
than or equal to
is
0, then by comparison, I don't know.
So the comparison limit says, if you can find some index, n1, in our case it's 1, if you can find some index such that from that index onwards, this inequality is true, then this converges to this.
Right.
So say that again. If I know An converges to A, and I can find some index n1 and some positive number C, so that this is always greater than or equal to this for that index onwards, then Bn converges to B.
Well, we already have our index if we know it converges, don't we?
Okay, how can I not confuse you with this? This index and this index are very different things. This is the index where something's less than epsilon. This index is where this is greater than or equal to this.
Okay.
So if we already know that this converges, right? And this thing is less than or equal to this thing from some point onwards, times a constant factor, then this thing also converges. That's the logic there.
And I see it. So that index is not index which makes it
Less than epsilon because there is no epsilon.
Right. It's the index that makes it greater than Bn minus B.
It's the index that makes this statement true.
Right.
I mean, the logic here is, look, if this distance goes to 0, okay, and this distance is always less than or equal to this distance, then this distance goes to 0.
Why
Which
should-
means that this converges.
Oh yeah, because it's a distance, obviously.
That's what it means for the distance to go to 0. The distance between B and Bn goes to 0. They get arbitrarily close. What does 1 over n converge to?
0.
Converges to 0 because 1 over n gets arbitrarily close to 0. What does 1 over n plus 1 converge to?
1.
1. 1 over n plus 1 gets arbitrarily close to 1. 1 plus a half is the first term, then 1 plus a third, then 1 plus a fourth, then 1 plus a fifth, then 1 plus a sixth, then 1 plus a seventh, then 1 plus an eighth, all the way down to 1 plus such a small number, it's as close to 0 as 1. Right? So, if this distance goes to 0, as a gets really, really big, then this distance goes to 0 if this inequality is always true, starting at some index onward. If there comes a point where this distance is always less than this distance, and I know that this distance eventually goes to 0, then this distance has to eventually go to 0. How's that? Does that make it click?
Okay, so explain the bottom line right here.
Well, let's make sure the comparison limit makes sense first, because it just uses a comparison limit. So if AN converges to A, then that means that the distance between AN and A gets arbitrarily small, right? It goes to 0. That's what we're saying up here. If AN converges to A, then for any really, really small number you pick, there's eventually an index where that distance is always less than that really, really small number.
Okay, my question is, so right there, you have an minus a, that, say, if we use 1 over n, it gets arbitrarily close to 0, right?
Uh-huh.
So you have a constant times 0, which is 0. So you're saying Bn either has to be 0 or less than 0.
What can I plug in here? Whose absolute value is less than 0?
Only 0.
Only 0! So Bn minus b has to get arbitrarily close to 0.
But what
Which
if
means
it was
Bn
1?
has to get closer and closer to b.
But what if it was 1?
What if what was 1?
What if an went to 1 and then you just have it
If an went to 1, then we're saying a is 1.
Yes.
What's 1 minus 1?
Okay.
This distance is the distance between the two. The distance between an and a goes to 0. That's what we mean. We mean an gets closer and closer and closer to a. This is the distance between them.
But what if it doesn't get closer and closer to a?
Then it doesn't converge to a. That's what it
Okay,
means.
but what if it
Converge to
doesn't
A.
have to go to 0? What if it converges to 1?
If an converges to 1,
Yes.
then you're saying this gets closer and closer to 1,
Yes.
and this is 1.
Yes.
So the distance between them.
So you're saying that can only be 0?
I'm saying that if an converges to a, then the distance between them is less than any positive number you can think of, no matter how small, starting at some index.
So the distance will always be
The
0.
distance approaches 0 because you can pick really, really small numbers there. You can pick 0.0000001.
So you're saying it does not matter what it converges to. It will go to 0.
I'm saying it doesn't matter what epsilon you pick. I can find an index in the sequence such that the distance is less than that small number you pick.
Well, yeah, by your community property. But my point is, what? Okay, I am so confused because that's a distance, right?
You're saying this?
Yes, that's a distance.
Yes.
Okay, are you saying that that distance always goes to 0? Because if you have your limit minus what you're converging to, it's always going to equal 0.
If an converges to a,
Okay.
then this distance always gets arbitrarily small. It always approaches 0.
So if it converges, it's always going to converge to, or it's always going to go to 0.
If an converges to a,
Okay.
their difference, or the distance between them, is always going to approach 0. It's always going to be less than any small number you can think of from some index onward.
Even if it converges to a billion.
Even if it converges, sure. Let's do one real quick. Prove that the limit of, what's something that converges to a billion? We can just do a simple one, like 1 over n plus a billion. Right? Prove that the limit of that is 1 billion. Right?
Okay.
So let's prove that.
Okay, it makes sense because that makes sense to me. But you're saying saying it's always going to be 0.
Well, how are we going to prove this?
Well, you could.
1. Let epsilon be any positive number. Right? 2. By Archimedean property, there exists some index n, or some number n, some natural number n, such that 1 over n is less than epsilon.
Okay. Yeah.
The distance between these two things
Yes.
Is 1 over n.
is always, I can always find an index where that's less than epsilon from that index onward. So this distance approaches 0. Gets closer and closer to 0. The
Yes.
bigger and bigger n I plug in there, the closer and closer this gets to 0. The bigger and bigger n I plug in there, the closer and closer this gets to 0.
And if that gets to 0 and you times it by anything, it's going to be 0. So that is also 0.
Right. So if this gets closer and closer to 0, if I multiply it by something, the product still gets closer and closer to 0. And if this is always less than or equal to this, starting at some index, then this also has to get closer and closer to 0. And the only way that this gets closer and closer to 0 is if this gets closer and closer to b. Which means this converges to b.
Yes.
Yes!
Okay.
Yes! Okay, wonderful! We got it! We good? We understand how the comparison lemma works, the logic behind it. And if you're still confused by it, go rewatch the proof of it. It's the best way to make sure you understand it is if you can sit down without looking, reproduce the proof, chances are you understand it. Okay, so now we're just going to use a comparison lemma. So we need to use a convergent series that we know, something that we know converges, to prove that something that we don't know converges does converge. Right? Remember that the comparison lemma is all about proving that Bn converges to B. So we already know An converges to A. We're trying to show that Bn converges to B. And Bn converges to B if Bn minus B is less than or equal to C times An minus A, starting at some index.
Why do you have to start at 1?
We didn't have to start 1, we could start anywhere. This statement is always true.
Okay.
But maybe it wasn't true for 1 and 2. Maybe you have to start at 3. Doesn't matter. As long as I can find an index where this is less than or equal to this, from that point onwards, then I know, since this goes to 0, that has to go to 0. Did we just undo all the work we did?
No. Okay, so, and then you have, on the second line, you have your alpha.
Alpha, absolute value of alpha is my C.
Yeah?
Alpha minus An is my B, N. Alpha minus A is my B. An is my An. A is my A. 1 is my big N.
Okay.
Or did I say N1? 1 is my N1. So this absolute value is less than or equal to this for all natural numbers starting at 1, which is all natural numbers. This says Bn converges to B if this is always less than or equal to this for all natural numbers starting at some natural number.
Okay. My question now is, can you prove that alpha will converge?
Alpha is a constant. Alpha converges to alpha.
Don't you remember?
Alpha is a constant. What is the limit of this sequence?
It's going to be alpha.
It's alpha.
Okay.
The limit of the constant is just a constant. Alpha is just a constant. It's just some number. Remember, A over N is constantly changing. Every time you plug in an N, you get a different Well, not necessarily, but it's potentially changing. Good? I mean, this is just using the comparison limit directly. This should be like a, oh duh, type proof. Well, if it's not an oh duh type proof, then I'm guessing you need to re-go over the proof of the comparison limit and then do that proof yourself. Because this is an oh duh proof from the comparison limit. So if you understand the comparison limit, doing this proof should be nothing. It's oh duh. So if this isn't oh duh, you need to go rewatch the derivation of the comparison limit. And make sure you understand that proof. The best way to make sure you understand the proof is, can you reproduce it yourself without looking at something? That's the best demonstration to yourself that you actually understand something instead of you just remembered what I did. Or it just makes sense when someone else says it. Okay. So are we good with that proof? A lot of work for a two-liner. It sounds like we made some progress that we need to make in terms of what we mean by a limit or a convergent sequence. Okay, moving on. Special case of the product of a limit is the limit of the product. We're going to prove a special case and we'll prove it in general. We're going to prove that the limit, well, special case, so let me write the special case we're talking about. If the limit of a(n) is equal to 0 and the limit of bn is equal to 0, then the limit of a(n) times bn is equal to 0. So we're going to prove this special case, and we're going to use it to help us prove that the limit of a(n) times bn is a times b. But we're going to start out with the special case. Okay?
Okay.
So this is just going to help us in our next proof. It's more of a little lemon. Real quick.
Oh my goodness. Yeah, clearly.
If this gets closer and closer to 0, and this gets closer and closer to 0, then their product gets closer and closer to 0.
Yeah.
Well, you say
Well,
clearly.
that looks obvious, does it not?
We're careful with the word obvious.
It looks.
Did I already tell you guys the thing about Leibniz?
About what?
Leibniz, when he was coming up with calculus, I think it was for something like 5 days in his journal he had recorded, and obviously the product of, or the limit, not the limit, the derivative of a product is a product of the derivatives.
That's not true.
Which isn't true. Do you remember the product rule for derivatives?
Yeah.
Okay, and we'll prove what that is later. But that's Leibniz. And who are we compared to him? We're nobody. So if he can screw up with what's obvious, we can screw up with what's obvious. So things might seem obvious, and if they're obvious, good. Means you should be able to prove it, right?
Mm-hmm.
Alright. So, no, that's it. Okay. 1. Let epsilon be some positive real number. And maybe I'll write down at the very bottom what we're trying to prove so that you can keep track of where we're going. We're trying to prove, therefore, the limit of a(n) times bn is equal to 0. When will this statement be true?
When a(n minus a is less than epsilon.
a(n) times bn minus 0 is less than epsilon starting at some index, big N. So we still need to find out what that index is, but here's what we're trying to show, right?
Mm-hmm.
Well, I know that this converges to this and this converges to this, so let's record that information. And what do you think I'm going to be doing? I'm going to be taking a product of these two things, right?
Yeah.
So I'm going to keep that in mind. If I'm going to be taking a product of their things, and I know that they're going to be less than any positive number I want, the positive number I want to make them less than is the square root of epsilon.
Right.
That way when I multiply them together, I get epsilon. Because I want epsilon to come out in the end.
Right.
So, since the limit then there must be some index called n1.
That's that. Or in natural number.
Too late.
-0.
Thank you. Having a hard time.
So when you manipulate your epsilon, you have to make sure that your epsilon stays a real number, right? That's the only.
Epsilon is a positive real number.
Okay.
Square root of ampersand.
Right? Since this converges to 0, then there has to be some index where that distance is less than any positive real number I picked, starting at some index. Similarly with this.
Right.
Mm-hmm.
And maybe I'll put let n equal the max of n1 and n2. Then so the value of an minus 0 is less than the square root of epsilon for all n greater than or equal to n, and the absolute value of bn minus 0 is less than the square root of epsilon for all n greater than or equal to n. Right? In other words, if this inequality is true from n1 onwards, and this inequality is true from n2 onwards, then both these inequalities are true from n onwards if it's the bigger of these two. Right? If this is true from 7 onwards and this is true from 14 onwards, then n is 14, and so both of them are true from 14 onwards. That's kind of the thinking there. Does that make sense? Okay. Alright, now we do our algebra. We need to manipulate this looking thing, and we need these things to come out of it. So I've got then an times bn minus 0. Now I need to manipulate so that these things come out. Well, that's equal to, first off, get rid of that minus 0. That might be confusing me. And then the absolute value of a product is equal to the product of the absolute values.
Yeah. And that's also equal to, obviously.
Which is also equal to, we can subtract 0 from that, we can subtract 0 from that. And that is less than square root of epsilon times the square root of epsilon is equal to epsilon for all n greater than or equal to big N. So there's the whole crux of the proof, that one line that combines everything we've been talking about. And we're done. Any questions about it? Any parts that feel weird? Just need more time to write? We good, James? All right. We're actually going to assume something here that you're going to prove for your homework. Real easy to prove. But from here on out for the rest of these proofs, I may use a fact that if the limit of an is equal to a, sorry, that was a terrible A. That is logically equivalent to the limit of an minus a is equal to 0. This and this say the exact same thing. Does that make intuitive sense?
Mm-hmm.
The limit of this equals that, and the limit of this equals that. And this is going to be a homework problem that you do. And you just plug that right into the definition and start playing with it a little bit until you get what this would be. My recommendation would be plug this into the definition, plug this into the definition, and see how you can connect those. Real easy once you write it out. I think you'll be able to do it. So we're going to use that fact for some of our proofs from here on. Because sometimes it's easier to prove this than it is to prove this. Well, I shouldn't say easier to prove. Sometimes it just, one of those pops out at you better. Yeah, because it's real easy to switch back and forth when you just plug in the definitions. I think you'll be able to do it. Okay, so now let's do our general proof. The product property. We're going to prove that the product of the limits, or that the limit of the products is the product of the limits.
Why is 2.2 so much smaller than 2.1?
Well, it's broken up by logic and material you need to cover. You don't just like write out the textbook and then say, okay, let's put a section every 30 pages.
Yeah.
So some concepts are easier, some concepts take more explaining.
2.1 is bigger than both 2.2 and 2.2.
Yeah, 2.1 is where we introduce this definition, and as you can see, this definition is a big deal. And wrapping your head around that is not trivial. So 2.1 is all about wrapping your head around that definition, making sure you understand it. Alright, so let's do this proof. That the limit of the product is the product of the limit. Once again, I'm assuming that the limit of this exists and the limit of this exists, or in other words, that these converge. I forgot to write that again, should have written it. If A and B are convergent sequences, then this limit equals this limit. Okay? Alright, one. Let A equal whatever A converges to. Let B equal whatever Bn converges to. And let epsilon be some positive number. With me so far? Nothing fancy? So, remember what we're ultimately trying to show. Maybe do a little bit of scratch work up here. We're trying to show that which way did I write it here? Oh, yeah, that's why I specified. We're trying to show that the limit of an times bn minus ab is equal to 0. Now you're saying, that's a little bit weird. Aren't you trying to show that the limit of an times bn equals ab?
Yeah.
Yeah, that's what we're trying to show. This is the same thing, and you're going to show in your homework that those two things say the same thing. So I'm now using this idea, and I'm going to prove that.
Oh, okay.
So I'm going to prove this version of it instead of this version of it.
Why?
Because I can. Just to make you have to think harder about it.
For funsies.
Well, it's more for the W's, but these are
But it's not for why.
I have what? Do you need sent to the principal's office?
Yes.
Okay, you can go with me.
You can go, dude.
Okay. Sorry. Two. So I'm going to come up with a new sequence called alpha n and beta n that converge to 0. I know converge to 0. Let alpha n equal an minus a. And equal bn minus b. Now this might seem a little bit weird until you realize that I'm going to be using this fact over here. So I'm trying to come up with two sequences that converge to 0. Because then their product converges to 0.
Why don't you just say that those converge to 0?
That this converges to 0?
Yeah, instead of putting it in the alpha n and the beta n.
I could have just used these directly. I think the only reason that you do equals is so that you can mess with something smaller.
Okay?
Help capture your logic while your reader through what you're doing. So, do I know that this converges to 0?
Yeah,
How do I know that?
because of that.
I know that this converges to b. How do I know that this converges to 0?
Right there.
Oh, right over there. Using that fact again. So we're using that fact again right here. We're going to use that fact again to realize these two things converge to 0. Right? Just making sure you see big picture what we're doing. Maybe it'd be better if I wrote it out and then made all these comments out now. So let's see. Let alpha n equal that, beta n equal that, comma, and maybe we'll try it out. And observe that the limit of alpha, not a, I don't like those braces though. I think it reads better if you say it like this. Let a n equal alpha n equal a n minus a, beta n equal b minus b. And observe that that sequence converges to 0 and that sequence converges to 0. Okay, everything there makes sense so far, right?
The product of them also converges to 0.
Well, if we can show the product of them equals 0, then we're done.
Right.
Because showing that the product of them, well, hold on. Because we need to take their product and we're going to get something that looks like this. But that's not all we're going to get. So, I'll just write it out and then you'll see. So,
Three.
Thank you. Just trying to find my place and write at the same time. So, I said that. Okay. Then, a_n times bn minus a times b is equal to alpha n plus a, beta n plus b, minus ab, well, I'm just doing algebra, so let me make sure you're following. Okay, ultimately, maybe come right. I didn't want to do my last line because I didn't know where it was going to be. But what am I trying to get to all the way down here? I'm trying to get that. Well, how am I even going to write it? Because I'm going to use. This is ultimately going to be my last line, right?
Yes.
And so I know that I need this an times bn minus ab is equal to something, right? I'm trying to show that that's equal to 0.
Yeah.
Okay?
Okay? So I'm going to have to start with this, and I need to plug in my alphas and betas somehow. So an times bn minus ab, that's this thing right here, right? I'm going to ultimately be talking about its limit, but that is equal to this, right? Alpha is an minus a, so an is alpha n plus a, and bn is beta n plus b. So that's plugging in for an, that's plugging in for bn, and then this is still just remainder.
And that was genius.
Good?
Yeah.
So now I got my alpha n in there, my beta n in there, which I know their limit is 0, right? Distribute. Oops. So I'm going to get alpha n times beta n. I'm going to get a times beta n. I'm going to get b times alpha n. I'm going to get a times b minus a times b, so those go out.
Yeah. Well, we know constant of a limit. Constant.
So that was just algebraic. Now I'm going to take the limit.
Well, all of those equal 0, don't they?
Right. Then the limit of an times bn minus ab
Plus.
is equal to the limit of alpha n beta n plus a beta n plus b alpha n
Equal to the limit of the individual parts.
is equal to the limit of alpha n beta n plus the limit of
Alpha, beta, n.
a beta n
Okay,
plus the limit of b alpha n is equal to. Okay, so far I use the fact that we know that the sum, or sorry, the limit of the sum is equal to the sums of the limits. Same thing we did over here. That's using this. The point of this, the reason that we're establishing these properties is like you don't have to go through finding the epsilon over and over again to show that the limit of something is something. You with me?
Yeah.
So you'll notice in this proof we're never going to do the epsilon anymore. Well, we may do it later.
Find the index.
Yeah, so there's none of that. We're just using things that we already knew converged. Okay, so I know that the limit of the sum is equal to the sum of the limits. This is a limit of two sequences that converge to 0. Right? So using this, I know that this is 0. This, I know that the limit of a constant times a sequence is equal to that constant times the limit of the sequence, which is 0, but we'll take time to spell it out. Same thing with this thing.
Therefore,
Done.
alpha
In case the reader lost track of what we were doing. Any questions? Any things that seem weird, funky, don't see it, needs more explanation? Maybe you can see where I drew Waldo. You have to look closely, he's hiding.
Yeah.
What?
I need refresh on why we're using them like that.
it equals 0.
No, well,
No, my question is,
like read your last statement. Therefore, the limit of an times bn minus ab equals 0. Oh, it's because of that. It's because of that.
Yeah, this.
oh,
Okay.
So I was trying to prove this. I rewrote it this way, I proved this, and therefore this. Any other questions? Feel like you got it?
Yeah,
Yeah.
most definitely.
Alright.
When we're trying to prove that something converges to, something has a limit, then we use the definition and we do like a proof like that.
Whoa.
A proof like this.
Yeah.
You can do a proof like this.
But you
Yeah.
can do other ways, but you're using the definition to prove it correct, right?
Chances are you're going to have to use the definition directly if you're given a particular sequence. Here I was proving something in general.
Yeah.
And I was able to use other general facts which I used, which had already found my epsilon for me. See, I was using this logic over here, where I had already found my epsilon and my index at work. And I was using this logic over here, where I had already found my index and my epsilon at work. And then this was just already using these two things.
But
So ultimately, it comes back to this direct definition. We use that definition directly here, we use that definition directly here, and we use that definition directly when we prove this. And then we combine this thinking, and this thinking to give us this thinking.
So if they have us find a limit of a specific function, then we use the definition.
You can always use the definition directly. You'll never go wrong using the definition directly. We could have gone back to the definition directly and proved this. It's just that we would have ended up coming up with thinking like this, coming up with thinking like this, and coming up with the type of thinking that you're using here. Probably.
Okay.
So you can always use the definition directly, but sometimes you don't need to. And when don't you need to? When you can just use these properties directly.
Yeah.
I mean, maybe you already know that 1 over n converges to 0, right? So maybe the author says, given that that equals 0 and that equals 0, prove that equals 0.
You use the.
And you could just use the definition directly and prove this. Exactly how we did right here. Or you could say, well, since that equals 0 and that equals 0, we have this lemma over one more. That tells us that the product of the two equals 0, right? When you view this as that time step. So you could use that over there. Or you could have proved it directly using the definition.
Can't we just, if we're given this, can't we just say because of this, then that? And we don't really have, or do we have to like write out?
You don't have to
Using the
reprove it.
specific.
You say from whatever the name of this is in your book, we know that the product of two limits that equal 0 is 0.
Okay.
I said that wrong, but I think you understood my thinking.
Yeah.
Yeah.
If our homework says, if the sequence AN converges, that's literally saying the limit of AN equals A, right?
I've got all the markers over in here. Someone actually throw them away.
What are you saying, Jake?
Oh, God. What the heck? When you make out markers, did you get like 4? No, there's only 2 in here?
I don't know why they make markers. That's literally like a academic.
Anyway.
Should be using these just buy it.
Just buy $100 markers. $100 plus.
We're almost to the end of this section. So we're filled with homework, so feel free to go on break and I'll start getting ready for the next couple groups.
What week is it, Jim?
6. Week 7.
We've had 7 classes, but I think it's 6.
Yeah, it's week 6.
We're barely finishing week 4.
You have class this Friday?
We had it last Friday, but not this class. We had Wednesday classes.
Oh, you rotate?
Yeah. Just
Yeah, so
works.
next third week we're gonna have Thursday classes.
And then that's the last time we had.
And then we have Monday classes for
Nah.
December.
Well,
Brother Hammond said.
Hammond
yeah, the
decided not to.
chances.
Actually, see, see.
He said
He said we're not going. drive never go up to Tech Ridge?
That's where we work.
I know, but I thought you work at home.
Oh, yeah, I sometimes do.
Like once a week.
Probably more like twice a week.
Do you hate the drive?
Very much so.
Why? Like listen to a book show.
Do.
You do?
Yep.
You take your Ford or do you take your what's your other car? Nissan.
I typically take my Corolla.
Is that the beat up one?
Yeah.
It's not a Camry.
No. Camrys are bigger.
Needs more fuel.
I did work with a busy one time. Like actually a bunch. They have a bald guy. He's a genius.
What?
What's your bald guy's name?
I don't know the bald guy you're talking about. The bald guy.
Paul
Let's see.
and bald.
What was his name? Dave?
I don't know.
The one who like manages tech rate stuff instead of busy stuff. Yeah. His name's Dave.
Izzy, stop being so soft. Oh!
That's from last time. I think
Oh,
you
I
saved
was
the other
like,
He wrote
wow, you wrote a lot. I need to go change my name.
Mark, what does that squeezer do for
You
you?
wanna know what makes me so mad?
Aaron Rodgers getting
Actually,
6 touchdowns.
Bigger thing, man.
Pissing me off.
Stuff like.
Dude, Aaron Rodgers got 6 touchdowns without one catch.
Why does it right
No,
now
he
matter?
got 7.
6.
It's
No,
probably
when? Yesterday?
pulling
Last
your
yesterday.
No, he got 5
Yeah,
out
but
of
why do you
6.
want to strengthen it? Is my
He
point.
got
your forearm.
Yeah.
5 passing touchdowns, 1 rushing touchdown. For total 6 touchdowns.
Yeah, ever do this in line?
Yeah, Devontae Adams probably is.
Yeah,
By
I'm
working that, you increase that strength.
I do want to increase
What
the
is short
strength.
top?
This
That's what
thing
he's
or
got.
something.
Yeah.
Alright, we all here?
No, you want to have it.
Yeah, yeah,
Your
sure.
grip, isn't it?
I don't know what that is. What is that?
I don't know what's what. They
Think
sound
I
broken.
can funny. I don't want my hand to let go of that. I want to hold.
Okay.
Alright. So this next proof, we kind of need to do a small little lemma first to prove it. You can often combine these into two, but I don't like that. I think they're better off separate. So ultimately, what we're trying to show is that if the limit of bn is equal to b, then the limit of 1 over bn is equal to 1 over b. Okay? And we got to do a little side proof to help us with that.
Okay.
So this is ultimately what we're trying to prove. The author has these combined into one big proof. I like it better separated.
You're saying when b is not, the limit is not 0.
Yeah, where b is not 0, then if the limit of bn equals b, then the limit of 1 over bn equals 1 over b.
Okay,
b can't be 0 because then
that'd be it.
undefined. Yes. Okay. So let's do the side proof that we need. So the side proof that we need is if the limit of bn equals b, where b is not 0, sorry I forgot to write that, then there is some index such that the absolute value of bn is greater than half of what it converges to, the absolute value of half of what it converges to.
Okay.
So this should kind of make intuitive sense, but let me try and help you for a second. So now let's think about that plotting the points of bn, and here's b, okay? I know that the points of bn eventually get to b, right? So I'm plotting them along, and we're eventually getting closer and closer to b, right? If I were to plot the points of bn. We're saying eventually bn is going to be greater than half of b. So eventually it's going to be in this range, essentially, is what we're saying.
After.
Absolute value of each.
Yeah, which is going to be equivalent to saying eventually these terms get within this range. From some point onwards, are always within this range.
So RB over 2 is playing as the same thing as our epsilon?
Kind of. You'll see how it comes out. It's a little bit trickier than that because obviously that's not exactly what
Epsilon is saying.
What we're saying, but yeah, we're going to find out when you let this absolute value of b over 2 be your epsilon, then you're able to prove it. So good intuition there, but it's a little bit more complex for proving than that. So let's go over it. So first off, observe that the absolute value of b over 2 is greater than 0, which means we can use it as an epsilon, right?
The requirements of epsilon.
Yeah, it fits the requirements of epsilon.
All epsilon is a positive real.
Epsilon is just positive real number. There's a positive real number. So we know that there must be some index n so that this distance is less than our epsilon, right? For all indexes onwards.
This
So
actually
we're all
helps.
good up to line 2.
Mm-hmm.
All right. Now I'm just going to break down this inequality. That's the same thing as negative what's on the right-hand side is less than this is less than positive what's on the right-hand side.
Yeah.
So we've gone from that to this a bunch of times. Hopefully you're comfortable with it now. And I'm going to do one more thing because for my proof I want b by itself. So I'm going to add b to both sides.
Right.
Okay? Now here comes the whole trick of the proof. Observe that b and bn have the same sign for n greater than or equal to n. So here's where you need to understand it. So either b is negative or b is positive, right?
Yeah.
Okay.
One of those two things. If b is positive, then eventually the b ends have to get within b halves of this thing, right? So it's impossible for them to be over here. It's impossible for them to be negative.
Well, yeah, I thought it has to be impossible just because it's absolute values.
Well, I'm talking about the bn's now. I'm not talking about the absolute value of bn. I'm talking about the bn's in general. So if b is a positive number, then for all my bn's starting at this index n, because remember, from n onwards, my bn's have to be within b halves of b, right?
Right.
So either they're over here or they're over here. But it's impossible for my b to be over here and have some bn's over here, or my b to be over here and have some bn's over here.
Right.
So either...
B halves never include 0.
Right. So from our index onwards that we chose, we know that all our bn's are either here or all our bn's are either here. If b is positive, they're here. If b is negative, they're here. All that matters is that they have the same sign. Okay? That's the only insight that I'm trying to give you in this line. Can you understand that b and bn have the same sign? Does that make sense?
Yeah.
It does? Okay. So now we've got two cases. Either b is positive, and so all the bn's starting at that index are positive, or b is negative, and all the bn's starting at that index are negative. So I need to handle both cases to show that this is always true.
Okay.
Okay? So if the b is positive, then we have, I'm taking this half of the inequality right here.
Right.
Oh, sorry, the other half. This half of the inequality right here. See it?
Yeah.
So that, what's the absolute value of b if b is positive?
Negative b.
What's the absolute value of b if b is positive?
B.
It's just b, right? So that is that. You good with that, Lee?
Mm-hmm.
And then just doing algebra on the left-hand side gives us that. And then since b is positive, b is just the absolute value of b. And since bn is positive, it's the same thing as the absolute value of bn.
Okay.
And so we got the absolute value of bn is greater than the absolute value of b over 2. So we showed this for the case where b was positive. Now we need to show for the case where b is negative. If b is less than 0, this time we're going to use this half of the inequality.
Wait, on 5 you said if b is greater than or equal to 0. Just needs to be greater than.
Oh yeah, because b can't be 0. But still. If b is less than 0, then we're going to take this half of the inequality and just work with it. Right? So this is still true because this was always true no matter what. But now, when we take the absolute value of b, what do we get?
Negative b.
Negative b. Because now b is negative. What's the absolute value of negative 3? Negative 3. B is a negative number, so when you take its absolute value, you get negative b. So you good with here to here?
Mm-hmm.
Okay. Algebra combining those two.
One second. The definition of an absolute value is
This just blows my mind how much I struggle with this. The absolute value of x is equal to x if x is greater than or equal to 0, negative x if x is less than 0. Okay, absolute value of 3 is equal to 3. Absolute value of negative 3 is equal to negative 3.
oh yeah.
Okay?
Yeah.
So, since b is less than 0, its absolute value is negative b. So that got us from here to here.
Okay.
Right? Algebra combining those two terms gets us from here to here.
Same deal. Now we.
Multiply both sides by a negative, flips our inequality sign, and then this is the absolute value of bn, and this is the absolute value of b. And so once again, the absolute value of bn is greater than the absolute value of b over 2. So
You
therefore,
lost me there again too.
I did.
Yeah.
Were you good
And absolute value. It's a.
from here to here?
Yeah.
I'm just reversing it. I'm saying that negative 3 is equal to the absolute value of negative 3. Negative a negative number is equal to the absolute value of the negative number. Negative a negative number is equal to absolute value of the negative number. Negative 3 is equal to absolute value of negative 3.
Why do we know that Bn is negative?
Because
oh yeah, because we
it's
saw
less than.
observe that. Yeah.
B and Bn have the same sign. Here's when they're both positive. Here's when they're both negative. And we're done.
So we literally just did that whole proof just to prove this.
All we were trying to show was that starting at some index, Bn is greater than absolute value of b over 2, if Bn converges to b. That's all we were trying to do because we're going to use this down here, and so we can use the comparison limit. Okay? So this was all a side proof so that we can say starting at some index, this inequality is true. Okay?
Okay.
And how we're going to use this, by the way, is we're going to say that 1 over Bn is less than 2 over B. Just rewriting it. Right? If this is greater than this, then 1 divided by this is less than 1 divided by this.
Okay.
1 divided by this is this, 1 divided by this is this. Are you having trouble going from this to this?
1 divided by.
What? How do you do something divided by a fraction? 1 divided by 1/4 is the same as 1 times 4 over 1, right? 1 divided by absolute value of b over 2 is 1 times 2 over absolute value of b. Maybe you just not comfortable with the logic in general. How come if this is bigger than this and this is less than this?
No.
Right?
I'm good.
If that's a bigger number than that, then 1 over that is a smaller number than 1 over this. And 1 over this is this. Okay, you good? Because that's the one little substitution that we're going to need. I'm going to need this is less than that. It's ultimately what I'm going to need. So we're going to plug that in as we go. Okay, so now the proof we're trying to do. So if the limit of b sub n is equal to b, where b is not 0, then the limit of 1 over b sub n is equal to 1 over b. Okay, so observe that the limit of b sub n equals b. Oops. The limit of 1 over b sub n is equal to 1 over b. So what we're trying to prove is true if we can find a c and an index such that, oh, did I erase the comparison limit?
Yeah.
Because it was right here. Do you remember the comparison limit?
Yeah, if you can find
Yeah.
a limit
The absolute value of b
smaller
minus
than
n.
a limit already proven.
If
Less
there
than
exists
or equal to.
n and c, well, something along the lines of if
If there exists c less
The
or
limit
greater than or equal to 0.
of b sub n is equal to b, comma, oh wait, we're using a's here. The limit of a sub n is equal to a, comma, and if there exists n in n and c greater than 0, such that bn minus b is less than or equal to c times the absolute value of an minus a for all n greater than or equal to n, comma, then the limit of bn is equal to b. Okay, that's what the comparison is. So, if this converges to this, c is a positive number, and we can find an index that makes this inequality always true, then this converges to this. Remember? So that's what we're going to use over here. So I'm saying 1 over bn converges to 1 over b. If I can find my c and my n that make this less than or equal to this for all indexes greater than or equal to that n.
Right.
So ultimately, I'm trying to show that this is less than or equal to this for all n greater than some n. And then I'm done. By comparison. Okay? You with me so far? So ultimately, I'm trying to show this is less than or equal to this. So now I'm going to play around with this thing and see what it is. So 1 over bn minus 1 over b is bn minus b over bn times b, getting a common denominator, times this one top and bottom by b, this one top and bottom by bn.
Yeah.
So we just get a common denominator there, and then I factor out the denominator. That's all I've done so far. So this whole line is just algebraic manipulation. Nothing to do with limits, nothing to do with calculus, just algebraic manipulation. You good with line 2?
Mm-hmm.
Okay. And then by the previous proof, we know that there exists some natural number n such that b of n is greater than absolute value of b over 2. Right?
Mm-hmm.
And here's the substitution that we're going to use. That's saying the same thing as this, so I'm going to use that substitution. So then, 1 over bn minus 1 over b, which is equal to 1 over bn times bn minus b. 1 over bn is less than 2 over the absolute value of b. 1 over bn is less than 2 over absolute value of b times that other absolute value of b. Do you see how this is making the substitution? 1 over bn is now 2 over b, but then we also have that other b, so it's squared.
Okay.
And I could have put the squared inside the parentheses, inside the absolute value sign. Doesn't matter. Because squared is always positive. Are you good with this as our substitution?
Yeah.
Yes.
Okay. And there you go. This is a positive number.
Oh, yeah.
So we had 1 over bn minus 1 over b is less than, which means it's also less than or equal to. Could put that in there if we want. It's less than or equal to. So 1 over bn minus 1 over b is less than or equal to some constant times bn minus b for all n starting at some index. By the comparison lemma, since we know that this thing converges, this thing converges. And we're done.
That's cool.
I don't know, anything weird about that? I know you might feel weird about what was up here, but hopefully this stuff down here feels more straightforward. Good? Questions? Yeah, I can't hear you when you all talk at the same time. I feel like there's questions, but you're just not asking them, which isn't a good feeling.
My only,
Because I don't know where I'm confused, but I know I'm confused.
my only hiccup was the substitution of the 1 over the absolute value of bn is less than 2 over bn.
So on this line, should we write it down more clearly?
Yeah.
Okay, let's write it down clearly. So we have 1 over bn minus b, or 1 over b, right? How many times top and bottom of this by b, top and bottom of this by bn, to get a common denominator? So top and bottom of this by b gives me b over b times bn, and this one gives me minus, if I times top and bottom of that by bn, b times bn, right?
Okay.
Right? Right?
Yeah.
Mm-hmm. Okay. Maybe really break it down. How's that?
Okay.
Good? Just breaking that into 2 separate products. Now using this substitution.
Yeah. 2 over b.
Absolute value of 2 is just 2.
Over bn, right? Not over b.
No. 1 over bn is less than 2 over the absolute value of b. 1 over bn is less than 2 over the
1
absolute
over
value.
bn times 1 over b
Okay.
times b minus bn is less than.
Yeah, because you have to do both sides.
Right. This is equal to this, and this is less than this.
Oh, right.
So then this times this is equal to this times this. That was one of our proofs, right?
Yeah.
We had something along the lines of if C is less than D and A is a positive number, then AC is less than AB. So that gives us the B's in the bottom. That's a B squared. And we can put absolute values on, it doesn't matter. Anytime you square a positive number, anytime you take absolute value, positive number. So we could have just let that B squared, we didn't need the absolute value there. Right? So now we have this is less than or equal, maybe write it all in one line. So now we have 1bn minus 1 over b is less than or equal to 2 over b squared times b minus bn. We know that converges.
Right.
And we know that this is true for all n greater than or equal to n, the index that we found here. We knew that there was some index that made this inequality true
Because of the previous proof.
because of this one. This proof says that there is some index where this is true from that index onwards. So there is some index where this is true from that index onwards. Right? That's all we did. And that's comparison limit. That converges. This is less than or equal to this, starting at some index. This converges. We're done. Da-da-da-da. Still questions? Still confusion? Everything made perfect sense? You guys know that you have the midterm at the end of the year, which makes up your entire grade basically, right?
Yeah. Like,
And all I'm going to do is go pick problems like this and put it on there.
well, you pick homework problems.
No. I'll pick theorems that I prove in class.
You will.
Or homework problems.
Yeah.
So make sure you can do it all. No, I don't really know what I'm going to do. I can go with whatever I feel at the time. I might just pick the flat out problem from the very last chapter that we covered. Huh?
Tell. Do what you said. Do all homework problems.
Alright. So now we have that, we can finally prove the quotient property, which is now going to be nice and easy. We need to do a proof that.
Did we just prove right there?
No.
No, we just proved that.
We prove that Bn converges to B, 1 over Bn converges to 1 over B. We need to do a quotient property similar to this. If A n times B n, yeah. If the limit of the product is the product of the limits, we need to prove that the limit of an over bn is equal to the limit of an over the limit of bn, where the limit of an is equal to a, and the limit of bn is equal to b is not equal to 0. Something like that. Right? Same exact thing we did over there, except for now it's a quotient, and we make sure that whatever the limit of bn is, it's not 0.
Okay.
Good? So, lost my place. Here we are. I start by saying 1. Let the limit of an equal a and the limit of bn equal b, but we already know that. So observe that the limit of an over bn is equal to the limit of an times 1 over bn is equal to the limit of an times the limit of 1 over bn is equal to a times 1 over b is equal to a over b. And we're done. Give me a little bit of space over here. A times 1 over b is equal to a over b. And we're done.
Easy.
Right? We know that the limit of a product is the product of the limits. We know the limit of an equals a, and since the limit of bn equals b, where b is not 0, then the limit of 1 over bn equals 1 over b.
Oh my goodness.
So there we go. We proved all our limit properties. And then we can combine some of these if we want. This one's called the linearity property of limits. Well, it's just a combination of things that we've already said. It's like you don't have to keep referencing individual ones. Given real numbers alpha and beta, and that the limit of an is equal to a, and the limit of bn is equal to b. Maybe instead of given, say if that, comma, then the limit of alpha times an plus beta times bn is equal to alpha a times plus beta times b. Well, I guess the So let's prove this real quick. So if alpha and beta are real numbers, and we know the limit of an equals a and the limit of bn equals b, we need to prove that the limit of alpha times an plus beta times bn equals this. Observe that the limit of alpha times an plus beta times bn is equal to what?
Limit of alpha n plus the beta bn.
Right. Which is equal to alpha times the limit of an
plus beta times the limit of bn.
plus beta times the limit of en. And I don't know why he doesn't take it one more step forward and say just prove that this is equal to alpha a plus beta b. For some reason he doesn't take it that far. He just takes it to here. Anyways, that's called the linearity property.
Why is
So
it
now-
called that?
Huh?
Why is it called that?
What's the context that you have seen this in? Linearity, when something has linearity, what that means is that you don't know what a vector space is. It means that, I don't know how to say it without just saying. When you multiply, so if some set of things has the linearity property, then if you take two things in there and you add them together, you get something in there. If you take two things in there and you multiply them by a scalar constant and add things in and add them together, you still get things in there.
Okay.
So they're saying, I mean, this is how you would say it with a vector. Well,
You'd say the limit of an and the limit of bn are vectors in the vector space.
right.
And
If we knew that
their sum is in the vector space.
this, so we have, if v1 and v2 are vectors in the vector space, then we know that c times v1 plus c2 times v2 is a vector in the vector space.
And that,
I don't know, I'm not going to explain this good on the fly.
but that means linearity if you have that property in a vector space.
Yeah, linearity means you can multiply them by constants and add them together and you still get something that still is in that set.
Yeah.
I could show it with derivatives, but we're not there yet. I bet the author brings it up again when we get to derivatives, so you'll see a more concrete example of this. So we got that. One more proof. I think he leaves it for you as an exercise. And it is the proof that where p is a polynomial, that the limit as n goes to infinity, and this is a very important one, as we talked about the limits of a function as it approaches a point. Okay, so now p is some polynomial function. What do I mean by polynomial function? I mean, for example, p of x could equal 3 plus 2x squared plus 7x to the 9. There's a polynomial function. You with me on what a polynomial is? It's all all the powers are natural numbers. So this could be, in general, what's a polynomial? It can be a to the 0 times x to 0 plus a to the 1, x to the 1 plus a to the 2, x to 2 plus dot dot dot. If you can express a function this way, it's a polynomial, where these just represent any real numbers. And so in this case, a sub 0 is 3, a sub 1 is 0, a sub 2 is 2, and a sub 9 is 7. And all the other a subs, everything is 0. You with me on what a polynomial is?
Yeah.
So, what's he saying here? He's saying if you take some sequence and plug it into a polynomial, and then take the limit of the values that you would get out, that's the same thing as just taking the limit of the sequence first and then plugging it into the polynomial. So
this is how we get away from sequences being stuck.
well, this is going to introduce us to the idea of taking the limit of a function at a point.
Right.
That's what it's introducing us to. But so let's think about this. So I got my sequence a and I'll say it's just equal to 1 over n. We'll do that sequence, nice easy sequence. And let's think about polynomial. We'll do a nice easy one. We'll do p of x equals x squared, one that we're nice and used to. Okay? So then, this converges, let's see, what do we want to converge to? Let's say we want to do it at, what do we want our a to be?
1.
1? Okay, so we'll do 1 over n plus 1 is what our a n will be, right? Because then that will converge to 1. Okay? So we're saying, let's write out all the terms of our a n. Let's write out what this sequence is going to be. What's the first term?
1.
2. What's the next term?
1 half. 1 and 1 half.
3 halves. What's the next term?
We did this 1000. 1 plus 1/3, which is 4.
I mean, how could we have rewritten this? 2 over 1. 2 over 1, 3 over 2, 4 over 3.
5 over 4, 6 over 5.
So what we're saying is, so here's all the terms in an, right? Well, what's p of an?
It's a function where you plug all those into x.
Right, but it's still going to give us out a series. And that series is going to be 2 squared over 1 squared.
We have that.
So this one's 4. This next one is 9 fours. This next one is 16 nines. This next one is 25 sixteenths, right?
Yeah.
36 25ths. So we've got an, it converges. And we've got p of an, right? And we're going to show that the limit of p of an is just p of a.
No,
So we're saying this converges to 1. So this is going to converge to p of a, which, bad example, is also going to be 1.
Yeah.
Because
Yeah.
1 squared is
If
1.
it was 2, it would be 4.
Right. So we picked bad numbers, but do you see that this is going to converge to 1, and that this is going to converge to 1? So we're saying the limit of the sequence that you get here is just what would have happened if you would just plug the limit of that sequence in here. Sorry, there's 2 different sequences being mentioned here. If you take the limit of this sequence, the p's of the an's, then that gives you the same thing as the limit of this sequence plugged in for p.
So if our limit, or if our a was 2, then our other one.
Yeah, let's not make it 1 since that's causing confusion. Let's restart. And maybe we'll change this one up too as well. Let's take a polynomial. Let's make it 1 plus x squared. Okay?
Okay.
So there's a polynomial, 1 plus x squared. And let's pick an an that converges to 2. And an easy one that converges to do is just 1 over n plus 2, right?
Mm-hmm.
So now I'll try this one. What's the first term? Write it easy for you.
Yeah.
What's the next term?
2 plus 1/2, so 4 halves. No, 5 halves.
5 halves. What's the next one?
7
2 plus 1/3.
Almost.
7/4.
Not
5
quite.
thirds.
7/3. Next one is
9/4.
9/4. Oh, did you see the pattern?
Yeah. 11/5.
11/5.
You do good
Etc.
on an IQ test.
Huh?
You do good on an IQ test.
Take the bottom, multiply by 2, add 1. Right? Okay, so this is an, right? And this, the limit of this is equal to 2. Okay?
Okay.
So that's our an. Maybe right over here. Here's what our an is doing. Now let's look at our p of an. What's that doing? And we're looking at the limit of this. So limit of that, limit of this, is the same thing as the limit of, let's look at some of these things.
10.
When I plug 3 into there, I get 10. Perfect. When I plug,
25 over 4 plus 1 is.
yeah, so 29/4.
Yeah.
What are you plugging in for x?
I'm plugging in this one into here to get this. So maybe one more way I could write these is underneath this was P. So this term right here is A1, A2, A3, right? This term right here is P of A1, P of A2.
You're plugging
Right,
in
we're doing P of AN. Good? So now let's plug in A3. What do we get? 49 plus 9 is 58.
Yeah.
58 ninths.
58 ninths, not 59 eighths.
81/16.
81 sixteenths? No.
Plus
It's 97/16.
97 sixteenths. Let's see, 121 plus 25 is 146. And we're saying that this thing is going to converge to,
2.
no, 5.
Oh, yeah, okay.
It's getting closer and closer to 5. And think about it, what's 25 times 5? Well, that's not very close yet, is it?
That's 6. That's 6 plus 6 minus.
What?
We start at 10 and get just under 6 in that span.
Oh, yeah. So we started as high as 10. Here we're a little less than 6. But we're going to get closer and closer to 5. So if you plug in a really, really big number, find a really, really big AN, like AN 1000, A sub 1000, and plug in here, you're going to get something really close to 5. Okay?
So what this shows?
Well, I'm explaining to you what we're trying to prove and give you intuition for it. So I'm saying, pick a polynomial function p. It's anything. Here we're using 1 plus x squared. And pick some converging sequence an that converges to a. Then, the sequence p of an converges to the same thing as p of a. Right? So given some sequence an that converges, like this one, and given some polynomial function, like this one, then this sequence, p of an, converges to p of a. Are you following that logic?
Yeah.
This is kind of important, so asking questions that you have, because this is what's going to back our whole idea of finding the limit of a function at a point.
No, it does not make sense.
Okay,
Okay, so are you saying, okay, so we have
maybe this
A of
one.
n, so we have A of n, right, and the limit of it is A. So you're saying the limit of P of A of n
Yeah,
is P of A.
yeah.
But,
What's P of 2?
so, okay, so here we have this function right here.
AN, here's its sequence.
Mm-hmm.
Convergent.
P of A of N, here's its sequence.
So you're saying that the limit of P of A of N is
Uh-huh.
5. So P of A is 5.
Uh-huh. What's A? In this case, A is 2. What's
What is-
P of A? 5.
Oh, okay.
I'm
We're
like,
plugging it into the function.
yes! Yes, P is our function. It's a polynomial function. P is just some polynomial function.
Mm-hmm.
So, AN, that's a sequence. Right?
Mm-hmm.
Take AN, each of those AN terms, and plug them into this. And you get a different sequence. 3 becomes 10. 5 halves becomes 29 fourths. 7 thirds becomes 58 ninths, etc. So this is another sequence.
Mm-hmm.
AN was a sequence, P of AN is another sequence. Take the limit of that sequence, see what it converges to, and I'm saying it converges to just P of A.
So you're saying,
In other words, if we were trying to show it in a general way like this, I'm saying that the limit of f of A of n is equal to, so the limit of the function of a sequence is equal to the function of the limit of the sequence. But I'm only showing that this is true for special functions, polynomial functions. See how this says the limit of the product is equal to the product of the limits?
yeah.
We're saying that the limit of the function on the sequence is equal to the function on the limit of the sequence. For special functions, polynomial functions.
Mm-hmm.
No? Yeah? Think you got it? Think you understand what we're trying to prove? Ask questions if something's not clear.
Okay, so for example, if they don't give you, so let's say in this example, they give you the function, right? The polynomial, what it is. So 1 plus x squared. And they only give you what A of n converges to, the limit of A of n. Then you're saying you can find a point. You're saying you can find the limit of the function with the limit of the one you have before.
Look, let me show you how you've seen this type of thinking in action. You were asked in your calculus class, find the limit as x approaches 2 of f of x equal to x squared plus 1.
Yeah, then you.
And you came out and you said, oh, it's 5. Because you just plugged it in there.
Yeah.
Why does just plugging it in there work? How the heck is this using the idea of a limit that I erased and the definition of a limit? What? You said, well, 2 works when you plug it in there, so ta-da!
Yeah.
Instead of saying, well, look here's a limit that converges to 2. We've got this proof here, and therefore, the limit as whatever we're plugging in here goes to 2 is P of 2. Lo and behold, you can just say that that's f of 2.
Makes sense.
Yeah, it makes sense.
So over here, you were just using crap without proving it. Why could you do that?
I wish we could just go back to you just using crap.
Then you can start going back to that, yo. Start asking why crap works.
Yeah, as soon as you get far enough, you start wondering, well, why does that work?
Well, when I get
Or you just don't really understand this stuff. And then you ask a question. Well, you make the statement, I don't remember how to do that. Instead of thinking about just doing it, you say, I don't remember how to do that. Because you never understood it. You just memorized a set of rules that you're supposed to apply. And when you forget those rules that you memorized on how you're supposed to apply them, fat chance can't do it. If I were to ask you to find the derivative of a product or a quotient, you're sitting there trying to remember in your head, is it low d high minus high d low? What is it? Right? Instead of just really quick thinking, okay, I'm talking about the quotient. Talk about the derivative of a quotient, what is that? Oh yeah, that makes sense. Oh yeah. And you just use it. It's a really simple proof. Once we wrap our heads around what exactly it's saying, there's a sequence. We have a sequence. We apply a function, which happens to be a polynomial function, nice simple function. We apply a function to each term in the sequence, which gives us a new sequence. The limit of that new sequence is just equal to what I would have gotten if I would have just plugged the limit of the sequence into the function directly.
Okay, now I have a question.
Okay,
What if you don't have what if you don't use a polynomial function?
we're proving it for the special case of polynomial functions. How many times in your calculus class were you dealing with not a polynomial function? No, you were. You had sine functions,
No,
cosine
my sine
functions,
functions
square root functions.
at the end all the time.
But it was rare that you weren't working with a rational function, which is just a polynomial function over a polynomial function.
Yeah, but that's not always the case with a rational function. Right?
A rational function is always a polynomial function over a polynomial function.
I know, I'm saying you can't always do this to a rational function, so that's a good example. Right?
Well, we'll get to rational functions and what we can do. Because you have to be more careful there.
Right.
Because when you're doing it there, you're going to be taking the limit of the quotient
Plug in and get 0.
of polynomial functions. And then we can apply our quotient rule as well as this rule. So it gives us a lot for rational functions too. But let's just start by wrapping our heads around this. So does everyone feel like they understand what we're trying to prove?
Yeah.
Okay. So let's prove it. Oh, this proof isn't as small as I thought. Because it goes to the next page. And we're also doing a proof by induction. So I'm going to prove it for, maybe you don't know, do you know what the order of a polynomial is? It's the highest exponent.
Mm-hmm.
So an order 3 polynomial would be of the form,
X plus X 2.
sorry, a sub 0 plus a1 times x plus a2 plus a3. Right? All third order polynomials can be expressed this way. So I'm going to show it's true for 0 polynomials, for first degree polynomials, for second degree polynomials, for third degree polynomials, for polynomials of any nth degree. Okay? So I'm showing it. So my proof by induction is going to be like this. I'm going to prove it for a sub 0, x sub 0, plus a sub 1, x to the 1, plus dot dot dot, plus a sub n, x to the n. I'm going to show it's true from 1 all the way for all the natural numbers. For all n that you plug in there, going out that far.
And then proof by induction, you prove that one is in the or.
Yeah, I'm going to show that it's true when x is to the power of 1. I'm going to show if it's true for all the way to x to the power k, it's true for all the way to x to the power k plus 1. Therefore, it's true for all the way to the power of n for all natural numbers. So first thing, maybe I'll go back to writing a really verbose proof by induction, and we'll create our set A and prove that A is an inductive set.
Okay.
Type of thinking.
I feel like we did this ancient.
Yeah.
1. Let A be the set of all, I don't want to use x, little a, I guess. Let it be the set of all natural numbers such that, I don't have a shorthand for a polynomial of that degree. We'll just use limit. Such that the limit of I'm trying to come up with a notation for an nth degree polynomial. How did I do it here? Oh, I just used a subscript. Okay. So maybe I'll do that. Notation I'm going to use for this proof. I'm going to say p sub something. If it's p sub 2, then that means a sub 0, x sub 0, plus a sub 1, x sub 1, plus a sub 2, x, oops, squared to the 1 to the 0.
Why is that p sub 2 not p sub 1?
I'm going to call that p sub 2 because it goes all the way to x squared. It's a
Okay.
second order polynomial.
Right.
You good with that notation? Okay. So A is going to be the set of all natural numbers so that P of n at a n is equal to P of n at a. So I need to start out with, well, I'm assuming I've got some sequence. Oh, sugar. You understand that these a's here and these a's here are the same thing? Let me switch this to b, so we don't get confused by that. And this n isn't the same as this n. Let's pick something else. I don't know. J.
PJ.
PJ. I work with PJ. Alright. So A is a set of all natural numbers where I missed my stupid limit sign. Are you kidding me? Okay. So A is a set of all natural numbers so that when I take the limit of a polynomial of that jth order on the sequence Bn, it gives me the polynomial at the limit of the sequence Bn. Do you understand what J is?
Yeah.
So, for example, does it work when J is 0?
When your p is to the 0th term.
Yeah.
Doesn't matter. It's not in our. What's that?
So what is a p of 0? What is a 0 degree? What is a 0 degree polynomial?
0 x 0.
It's a to the 0, x to the 0, right?
Yeah.
Mm-hmm.
If x
Which is what?
1.
Okay.
That's 1, so it's just 1. So it's just a number. Any real number can be viewed as a 0th degree polynomial. 157 is a 0th degree polynomial. 2,988 is a 0th degree polynomial.
Right.
So, if I have some 0th degree polynomial, f of x equals 2, that's a 0th degree polynomial, right? We just have a constant.
Yeah.
Mm-hmm.
What do I get when I plug anything in this?
You get 2.
You get 2. So, the limit of the sequence as I plug it in there, which is always 2, 2, 2, 2, 2, is equal to 2. You see how it's obviously true?
Yeah.
Doesn't matter what we plug in there, p of anything is just equal to p of anything. So we have the limit of 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2 is equal to 2.
Yes.
So when it's sub-0, then we're saying the limit of a sub 0, 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 a sub 0 over and over again is just
A sub 0.
a sub 0. And it doesn't, the fact we're plugging b in doesn't matter.
But we, natural numbers, they have 0, so.
I know. So we need to show it's, I don't know if we're showing it starting at 1. Because we already know that the limit of a constant is just a constant of a limit. Or is just a constant. So we'll start this at 1 and work our way up. But so it's true for 0. Now let's think about it for 1.
Okay.
An example, this would be something like plus x.
The limit of x.
And notice what happens when we take the limit. So let's say that now we're plugging in some sequence b sub n, right?
Okay.
And so let's pick some b sub n. Let's do 1 over n. You with me? I'm just doing 1 over n. So when we do 1 over 1, what do we get?
1.
1 plus 2 is
3.
3. When we plug in 1 over 2, what do we get?
5x.
And we can keep doing this. But you're going to notice that's the same thing that we get if we put the 1 over n here, right? So you're just thinking about it this way. If we plug in 1 over n here, then that's plus 1 over n here. And so the limit of this thing is just the limit of this thing.
Mm-hmm.
Which is the limit of a constant plus the limit of 1 over n is 0, which is 2.
Right.
So that's going to end up giving us 2 again. So here's what I'm saying in general. Let me write out this case, kind of verbose. So if we've got p sub 1 of some sequence b of n, and we want the limit of this, let me rewrite this one more way. So we're looking at the limit as n goes to infinity of p sub, we'll handle the case of 1 now and see it written out. P sub 1, we're plugging in b in here, right? Well, that's equal to some constant a0 plus bn, well, some other constant a1 times bn. Right? Because p sub 1 of x is just equal to a sub 0 plus a sub 1 x, right?
Yeah.
So p sub 1 b of n is this thing, but we need the limit of that thing. So
Which is just b.
limit as n goes to infinity of a sub 0 plus a sub 1 x.
Which is just b.
Well, the limit of the sum is the sum of the limits.
Well, no, constant plus.
Oops, b sub n.
It also did that funny middle.
Oops, b sub n. Right?
Yeah.
So P1 represents a first degree polynomial. That's just a constant, we don't know what it is. That's just a constant, we don't know what it is. X is the variable that we plug in for. So then, the limit as n goes to infinity of a first order degree polynomial, when we plug in b sub b of n, is the same thing as the limit as n goes to infinity of a sub 0 plus a sub 1 times b sub n. We just plug in b sub n for x, right? And then the limit of a sum is the sum of the limits. And then, the limit of a constant is what?
A constant. The constant.
Just a constant. Do you know what I mean by the limit of a constant?
Yeah.
The limit of a sequence that never changes. It's just 2, 2, 2, 2, 2 all the way. So the limit of a sub 0, a sub 0, a sub 0 is just a sub 0. Plus, the limit of a constant times a sequence is the constant times the limit of the sequence.
Which is just b.
Perfect. Right?
Which is what our.
Which is exactly what we get if we just plug b into this. So maybe you write my last line, that's the same thing as p sub 1 of b.
Okay, so we proved the first one. How did we prove all of them today?
Right, so we just basically proved our base case.
Yeah.
But I just wanted to write it out very explicitly so that you can see it.
Now we gotta prove x plus 1, or case plus j plus 1.
So, kind of have my work all over the place on this proof, sorry about that. Try and clean up a little bit. 2. Observe that equals that, and so the limit of that equals that equals that equals that equals that. 3, therefore 1's an A.
Oh yeah, forgot we needed to know that.
Alright, so we know 1's an A. In other words, this statement is true for first degree polynomials. Is it true for second degree polynomials and third degree and all the rest?
now we show that.
We need to show if it's true for
Yeah.
k. If k is an a, then k plus 1 is an a.
Okay.
So assume k is an a. What number? 4? 4. Assume k is in a. What does it mean for k to be in a? No.
No.
We need to show if k is an a, then k plus 1 is
P
an
to
a.
the K.
But exactly what this means. It means that the limit as n goes to infinity of a kth degree polynomial of b sub n is equal to pk of b. Right?
Yes.
Okay. 6. Then
P plus K or P.
p of k plus 1 of b of n. We need to show that this equals p k plus 1 of b, right? But what is this? Maybe write out explicitly what this is,
Okay, P plus.
and I'll use sigma notation to help see what I'm thinking here. So this is equal to the sum from j equals 0 to k plus 1 of a sub j x to the j. Oh, x to the power of j. That's what a k plus 1 polynomial is. Do you see that? That means a sub 0 times x to the 0 plus a sub 1 times x to the 1 plus a sub 2 times x to the 2. Right? Are we for sure comfortable with that?
Mm-hmm.
For sure. Okay. Then that is equal to, check it, trick you guys have already used, j equal to 0 to k of a sub j x to the j plus
K. Or 1. K plus 1.
a to the k plus 1 x to the k plus 1.
Okay.
Sorry, I'm doing this different than you guys usually do it. Usually you start with this and you add k plus 1 to both sides. A sub k times k plus 1 to both sides. So sorry about that. But this still works, right?
Yeah.
So that's equal to that, equal to that. Pull out the last term.
Yeah.
I just pull out the last term of this. So now this used to be the sum from j equals 0 to k plus 1. Instead it's just the sum from j equals 0 to k, and then we wrote the k plus 1 by itself. Good?
Yeah.
Okay, so now let's take the limit. And the limit, as n goes to infinity, of p sub k plus 1 of b of n is equal to the limit as n goes to infinity. Oh, I should have written one more thing up here. Sorry. You guys have got to stop me from making these mistakes. That's not x. That's a b sub n
Yeah.
to the j. Because we plugged in b sub n for x, right? B sub n to the k plus 1. Okay, now that's equal to this one here is b sub n. You do with that? I'm just rewriting that. The same way I can go from that to that, I can go from this term to this term. And then this stays the same.
Yeah, that makes perfect sense.
Do you see it?
Yeah.
See it? Okay. So now the limit. So now the limit of this ink is equal to the limit of this ink. And then the limit of the sum is the sum of the limits. Sorry, maybe that's throwing you off. that's equal to the limit of, I won't bother with the brackets now since it's just one term, p sub k, b sub n, plus the limit, and I'll still do my brackets here. Right? We already know what the limit of this thing is, because k is an a.
Just A or B.
Yeah.
P of
A of B.
It's pk of b plus the limit of this thing. Well, what can we do with this? We can pull out the a of k plus 1, right?
Yeah.
And you just get your B.
Almost. We have a b to the power of k plus 1 n. Don't worry, we'll take care of it all as we go. Using our rules. Right?
Yeah.
Just the limit of a constant times a sequence is equal to a constant times the limit of the sequence. Right? And notice that this is a bunch of products now. This is b of n times b of n times b of n times b of n times b of n k plus 1 times. So the limit of the products is the same thing as the product of the limits. So make sure you understand this next line. P, K, B, that stays the same, but now it's plus a of k plus 1 times the limit as n goes to infinity of b sub n k plus 1 times. Let me do my
So you pulled out the k plus 1?
The limit of the products is the product of the limits.
Oh, okay.
What is it saying? It's saying the limit of a goes to infinity of b sub n times the limit of n goes to infinity of b sub n over and over again, k plus 1 times. This times this times this times this, over and over again, k plus 1 times. This in here we have b of n times b of n times b of n times b of n, k plus 1 times. This is the limit as n goes to infinity. It's the limit of b of n times the limit of b of n times the limit of b of n times the limit of b of n. That's what our product rule told us. The limit of the products is the product of the limits.
Okay.
You good with that? And then finally, well, not finally, almost there.